Hello, welcome back. This is Calculus by Dr. Oz. Today we're going to go over the integration of inverse trig functions, and we have three learning objectives to achieve today. And the first one is to integrate functions whose antiderivatives involve inverse trig functions. And the second one is to use the method of completing the square to integrate certain functions. And finally, we're going to review the basic integration rules involving elementary functions. All right, let's start with the first learning objective. That means we're looking at the functions whose antiderivatives involve trig functions. So let me just bring up this first slide here, which essentially says that if you start with the arcsine x function, and if you take the derivative of that, and we have the differentiation formula card, we know that the derivative is going to be 1 over radical 1 minus x squared. And if that's arc cosine x, you have the same type of derivative except the sign. So you have the negative version of the one here. Okay, so what that means is if you start with a function like that, and if you are interested in finding the antiderivative of it, and that should be arc sine x. So that's what we're going to use along the way. Okay, so I have three different formulas here. The first one is reserved for arcsine function. So essentially, in the bottom, you have a difference of squares. Here, u is a differentiable function of x, and a is a positive number. And as you see that you have a squared minus u squared, in fact, the radical of that in the denominator. So if you have an integral like this, that means you're talking about arcsine u over a type antiderivative. If you have a squared plus u squared in the bottom without any square root, that means you're talking about arctan type antiderivative. In fact, it's 1 over a arctan u over a. And finally, if you have in the bottom u and u squared minus a squared, and u comes before than a, by the way, u term comes before than a term, then you're talking about arcsecant type integrations. All right, let's practice these three formulas. Our first example is the integral of dx over radical 4 minus x squared. So this is very similar to the very first formula here because you have the difference of the squares in the bottom. And all we need to do is to put our integral in that form. So, well, first off, 4 is 2 squared, and I have x quantity squared. So if I take a to be exactly equal to 2 and u exactly equal to x, so in fact du even equals dx, right? If you want to make a u substitution like that, and you have u equals x, a equals u, so you have arcsine u over a, and you end up having arcsine x over 2 plus c. All right, let's check out the next example. It's dx over 2 plus 9x squared. And this looks like that we are in the second case here because we have a squared plus u squared in the bottom. So all we need to do is to convert our integral into this form. So, and how do we do that? Well, if you take a u to be 3x, because this is 3x quantity squared, and if you take a to be exactly equal to radical 2, because 2 is a radical 2 squared here. So now all I need to do is just looking at du, that's 3dx, and converting this integral to the du version of that. So dx is 1/3 du, so 1/3 du, and I have a squared plus u squared. So 1/3 out, you have du over a squared plus u squared. Okay, so going back to the formula again, so then you have du over a squared plus u squared. It's 1 over a arctan u over a. All right, so 1/3, we already have it. 1 over a arc tan u over a plus c. So all we need to do is just plug back a and u. So a equals radical 2, so this is 3 radical 2, arc tan 3x over radical 2 plus c. All right, let's look at the final example here. So we have dx over x, radical 4x squared minus 9. And this looks like we are going to use the formula 3 here. But we have to convert the given integral to the one in formula 3. So here we have 4x squared, that's 2x quantity squared. And I have 9 here, and that is 3 quantity squared. So that tells us exactly what u should be. So u equals 2x and a equals 3. And therefore du equals 2 dx by the u substitution. All right, so I have dx to be 1/2 du. I have x in the bottom. X is isolated, so x can be solved out of this formula. In fact, x equals u over 2. So here we go. I have u over 2, and then radical u squared minus a squared. All right. So the 2's cancel out, and this turns out to be du over u radical u squared minus a squared. That's the exact same pattern in formula 3. So the antiderivative should be 1 over a arc secant, so 1 over a arc secant, absolute value of u over a. Now let's plug u and a back here. So we have 1 over 3, don't forget the integrating constant here, 1 over 3 arc secant 2x over 3 plus c is the final answer here. And we also have the absolute value here. All right, we're done with the first learning objective. Please go ahead and check out the restation videos to practice all 3 formulas on different examples. So in the first one, you have 3 integrals to take care of, and some of which are using also u-substitution. And if you're rusty with u-substitution, this is the best time to play with it. And we have 3 examples here. Also, we have a definite integral versions of the same type of formulas being applied to these integrals. So please go ahead and check out. You have in total of 6 practice problems, and each of which has a video where you have the step-by-step explanation. All right, I'll see you in the next video. Bye.